Welcome everyone to another OGRA webinar. We are fortunate today to have Corrugated Steel Pipe Institute again here with us to present on drastically reducing your carbon footprint for culverts and storm sewers. I am Amin Menena and I will be your host and moderator. I'm the coordinator of technical products and research at the OGRA. We will start off on touching on a couple of housekeeping notes before we start the webinar. This webinar will be recorded and will be made available to everyone to view the recording on our YouTube channel, OGRA's YouTube channel. I will share a link to the YouTube channel in the chat. If you have any difficulties at any time, just type me a message in the chat and I will make sure to address your concern. We also encourage you to ask questions throughout the webinar, like during the presentations via the Q&A function. And we will, once we have time, we'll interrupt the presentation and ask your question live during the presentation. And we will hold more questions at the end of the webinar. So at the end of the webinar, if you wish to ask your question verbally, click the raise your hand button and I will turn on your microphone. You will be able to verbally ask your question. But with that, please make sure that you're concise and you don't take too much time with asking the question. Now it's my pleasure to introduce Ray Wilcock, Executive Director of the Corrugated Steel Pipe Institute. He holds a science diploma from Champlain College in 1978 and a Bachelor of Commerce from Concordia University, 1982. Over the past 3 decades, he has held a number of senior executive positions at several corporations in the infrastructure industry. We also have with us today Stan Lipowski, who is the metallurgical engineer and has been working at
ArcelorMittal.
Yeah. For 19 years, he started his career in the galvanizing and cold rolling lines before moving to the position in construction market development, where he acquired an experience in product sustainability. Stan is a Lifecycle Assessment LCA partner who has developed several environmental product declarations and whole building LCA codes studies. With that, I'd like to turn the floor over to Ray. Ray, the floor is yours.
Thank you, Amin, and welcome to each and every one of you this afternoon. I hope that you can all see my screen. What you should be seeing is the CSPI, Corrugated Steel Pipe Institute. This is our 60th anniversary. The CSPI commenced in 1961. The agenda today is I'm just going to spend a couple of minutes on the CSPI, and then I'm going to pass it over to Stan Lipkowski from ArcelorMittal, who's been introduced already. Stan's going to go through the life cycle of a product, steel production results, carbon reduction strategies, and then he's going to pass it back to me, and I'm just going to talk about the environmental product declaration results of corrugated steel pipe and structural plate. I'm going to do a comparison to reinforced concrete pipe. Show you a little bit about a carbon footprint calculator and just talk a bit about the future plans. Corrugated Steel Pipe Institute represents the manufacturers of corrugated steel pipe and structural plate. Armtec and Atlantic Industries are both national players with plants pretty well right across the country from Newfoundland to British Columbia. Hubcap and Frontier are both regional players. We also have in our membership ArcelorMittal, Dofasco out of Hamilton, the largest steel producer in the entire world, with I believe, and Stan can correct me on this, with something like 60 plants worldwide. We also have Ironside. They make machines. Leland Industries make nuts and bolts. Advanced Coil Industries and Warner Custom Coatings make coatings for material like polymer. AK Steel, a very large steel producer out of the United States. They make aluminized type 2 steel. We also have members outside of North America or outside of Canada, like Velfilm out of Brazil, 2xO, which is in Paris, France. Rondell and CMP is in Australia. Viacon out of Poland, Marmac out of South Carolina, and Birkenhoek in Amsterdam in the Netherlands. And we do a lot of sharing back and forth between the Europeans and the Australians. They learn from us, we learn from them, and we're very happy to have them in our small membership in the CSPI. So with that, I'm going to stop sharing and I'm going to mute myself and pass it over to Stan.
Thanks, Ray. Do you see my screen okay? Okay, I'll start off with a brief introduction on our company. ArcelorMittal, we're the world's largest steel and mining company. We employ 170,000 employees across the world, located in 19 countries. Our steel making capacity is 83 million tons annually and 118 million tons of iron ore production. Our key markets are in automotive, construction, household appliances, and packaging. And we also invest heavily in research and development. We have 200 employees working in R&D across 14 research centers around the world. Can you hear me okay? Oh.
Yes, we can,
Yeah.
Stan. We can hear you fine.
Can't go forward for some reason. It's not allowing me to flip. Oh, hold on. Am I in presentation? Yeah, I'm in presentation mode, but it's not allowing me to flip to the next slide.
One second. Let me share your presentation on my screen, and you can verbally tell me to flip the slides. One second. Let me bring it up. Please hold on, everyone, until we...
Actually, I was able to flip.
It's working
on my end, yeah.
All right, awesome.
What happened?
Sorry about that, everyone.
Sorry about
continue
that.
on, Stan.
So our footprint in Canada, we have 10,000 employees across Canada, 6,000 employees in Ontario. Our mining facilities are located in northern Quebec, as well as in the Northwest Territories, Baffin Island, very far north. And our steel manufacturing footprint is located in the Montreal area and in Hamilton. Our largest steel mill in Canada, the Fasco, is in Hamilton. So now I'll provide some background information about lifecycle assessment. Lifecycle assessment is a technique that assesses environmental impacts associated with all the stages of a product's life cycle. So this includes raw material extraction, manufacturing, transportation, the use, and very important for steel, the end of life recycling. Steel is one of the most recycled materials on the planet. And also LCA has become the most scientifically credible method of modeling the environmental impacts of a product. Now, to conduct a life cycle assessment, what you need is massive quantities of data. to give you an idea of how much data, when I collect the data for one of our products like hot to galvanized coil, it requires 1,000 input-output flows. Now, every single flow then has to be traced downstream all the way to the cradle, to an elementary flow. So for instance, at one process in our operations, I collect the quantity of electricity that's consumed. That has to be traced to our grid. And our grid is made up of different forms of electricity production, but let's say nuclear, for a portion of that is nuclear, for example, that has to be traced all the way down to the amount of uranium that's mined. So massive quantity of data is required, and that data is called lifecycle inventory data. The other thing that you need is standards that tell you how to conduct that lifecycle assessment, because in the end, these impacts have to be comparable. You have to be able to compare apples to apples. So you have to ensure that they abide by the same rules, and these standards are called product category rules. And an LCA is typically a very long report. It could be more than 100 pages long. And many people aren't interested in all that detail, so that's why they create EPDs. It's a one-page summary of a complex LCA report. It just lists several environmental impacts results associated with the life cycle of that product. So the EPDs have to abide by a long series of standards. The overarching standard for life cycle assessment is ISO 1444. Then there's ISO 1425 that deals with type 3 certifications of EPDs. ISO 21930 and EN 15884 are specific to the construction sector. And then there's product specific PCRs. So for the steel industry, we recently developed our product categories for steel for the North American market. And these have to be published every 5 years. So that was recently updated. Now, to give you an idea what's involved in modeling the life cycle of corrugated steel pipe, I pasted the screenshot of the LCA software I use, Gabby. So you can see I start off with a process for hot to galvanized coil. This is an industry average data set, so it includes the data that I've collected from our site for hot to galvanized coil, as well as others from other sites across North American steel industry. Then I modeled the transportation to our culvert manufacturers, and then the end-of-life recycling. Now, if I double-click on that culvert manufacturing process, I get the following information. So these are the input-output flows I collected from our customers. So based on 1 kilogram of hot galvanized coil, this is the amount of electricity, the amount of natural gas, propane, and so on. And on the output side, the amount of culverts produced, the amount of steel scrap that was lost during the manufacturing process. So then when I hit run in my LCA software, it outputs all the information necessary to create an EPD. And this is the EPD we published for corrugated steel pipe a few years ago. As you can see, there are several environmental impact categories and several numbers listed. So I won't go into detail. Ray's going to go into more detail in his presentation on these impact categories. But one number I really want to focus on is at 2.21, the amount of carbon emissions from steel production. This number is a big problem. And this slide shows why. It shows total global carbon emissions by sector. And as you can see, the steel industry emits 8% of total global carbon emissions. Other sectors like power and transportation, they have a bigger share. But in those sectors, there's a green light at the end of the tunnel. I mean, for the transportation sector, for instance, there's pioneers like Elon Musk that have led the way to electrify the transportation sector. And the power sector, there are renewable technologies like wind and solar that have become cheaper to produce than burning fossil fuels. But steel and cement, in those sectors, they're called the hard to abate. It's much more difficult to decarbonize those sectors. So it's a big challenge. But at ArcelorMittal, we we're a large company. We have the global scale. We have greater technical resources than many of our competitors. So we're very well positioned to lead the way to clean up our industry. Now, before I get into talking about our decarbonization strategy, first, I have to provide some background on how steel is produced today. So to produce today in the steel industry, it's produced using 3 technology routes. The first is the blast furnace. Here you use coal to reduce iron ore. This is by far the most energy efficient way of producing steel, but unfortunately it's the most carbon intensive way. So on average, globally, a blast furnace emits 2.3 tons of CO2 per ton of steel produced. Now, the other 2 technological pathways of producing steel are through the electric arc furnace. This is a technology that's been around for 100 years, but it became more prevalent in the 60s when greater stockpiles of scrap became available. But in an electric arc furnace, there are 2 feedstocks that you can feed into it. One is iron ore, but it's iron ore that's been reduced with natural gas. It's called DRI, directly reduced iron. And when you feed that into the electric arc furnace, your emissions are 1.5 tons of carbon per ton of steel produced. And then the other option is to make steel by melting scrap in an electric arc furnace. So here, the number drops to 0.8 tons of carbon per ton of steel produced. Now, these are world average numbers, and the distribution is quite large. At 1x, and the emissions here are totally dependent on the electricity grid. So they're scope 2 emissions. They're not direct emissions like the blast furnace or scope 1 emissions. So for instance, if you're on a grid like in China, that number will jump from 0.8 to 2, because in China, the grid is mostly produce electricity mostly by burning coal. But for instance, we have a mill in Quebec where the grid is completely decarbonized. So there, that number is dropped down to approximately 0.2. So it's what we call is practically carbon free steel. So you may ask, why don't we produce all steel by melting scrap? And this chart shows why. Last year, globally, we produced 2 million tons of steel, but scrap availability stood at 600 million tons. So we're predicting it will take about 70 years before, even because the amount of steel produced will continue to increase, demand for steel will increase. It will take 70 years before we have enough scrap available to theoretically produce all steel. So we're going to have to use iron ore to produce steel for a long period of time. And so we definitely have to decarbonize primary steel production to meet our Paris Agreement objective to be carbon neutral by 2050. So in 2019, we published our climate action report, and there we outlined how we plan on decarbonizing our primary steel production, and plan doing that using there's three pillars in our strategy. The first is clean power. We're going to need massive quantities of clean power to produce green hydrogen. The second is circular carbon, where we will be substituting our coal with bio-based materials and plastic. And the third is carbon capture and storage. We're going to have to capture our emissions and store them. So this slide goes into more detail about our smart carbon technology pathway. So we'll be feeding plastics or bio-based materials, so waste wood. So here in Ontario, we have massive quantities of wood going in our landfills from residential construction, demolition waste. So we'll be sending those materials, putting those materials in a pyrolysis process. From this process, we'll have high carbon, very high quality carbon product that we can feed into our blast furnaces. Then we'll be capturing that carbon, and we've partnered right now with a company called LanzaTech that it takes that carbon and through they use bacteria through this special, it's a fermentation process. They create ethanol, and ethanol can be used to create several things. It can be used to create fuels. But one of the applications, you can use ethanol to make plastics, so this is a truly circular process, because on the end of the life, that plastic can be recycled back into our blast furnace, and it solves another big issue environmentally, the plastic waste issue that we have, because plastic isn't a very recyclable material. But the problem with this technology is that it's not enough. Our blast furnaces emit far too much carbon, so it's only part of the solution. So this is how we envision our blast furnace of the future. We'll be feeding hydrogen into our blast furnace as well. And at first, this will be what's called blue hydrogen. So hydrogen has been color coded. The gray hydrogen is hydrogen produced from natural gas production. Blue hydrogen is hydrogen produced from natural gas, but the emissions are captured and stored. And then green hydrogen is the hydrogen produced using clean electricity. But we don't envision large quantities of green hydrogen being available until well after 2030. So until then, we'll be using blue hydrogen to feed into our blast furnaces. And then we'll be also using the circular carbon, a process that I've already described to you, and there'll still be some leftover emissions that we'll have to capture and store permanently. So now I'll talk about where we are currently. We have several pilot plants, primarily in Europe. So in Ghent, we have a Torero process plant. This is where we create biochar. And we have one reactor that will start operating in 2022, a second one in 2024. In Ghent as well, we have our steel node production. This is where we partnered with LanzaTech. We captured the emissions, and through that fermentation process, we'll be creating 80 million liters of recycled carbon ethanol. It's a 165 million euro investment, and production is well underway. It's a massive plant that they're building, and production is expected to start next year. In France, in Dunkirk, we have a project called EGAR, and this is using our coke oven gases, recycling our coke oven gases. So coke oven gas is very rich in hydrogen. It's I think 60% hydrogen. But we use it at most of our facilities we burn it and generate electricity. Use it to generate electricity. But that creates emissions. But the other option is to stop producing electricity with it and feed it into a blast furnace to significantly reduce the blast furnace emissions. And finally, we also have a carbon capture and storage in a project in France, and that's expected to start in 2021. So fully implemented, the smart carbon route so will result in 250 kilograms of carbon neutral cement. So our blast furnace produces a byproduct called slag. That slag is used today to make significant quantities of slag cement. But the problem with that slag is that it has a high carbon content. So now we'll be able to provide carbon-free slag to the cement industry so they can reduce their footprint. It also produce 200 kilograms of carbon neutral plastics. In one study, Europe has showed that if the entire steel industry converts to smart carbon, it'll be able to supply more than 60% of Europe's polyethylene-based plastic needs. And finally, because we're using biomass material, the steel can remove, we'll be able to remove carbon from the atmosphere, because we're using biomass, and then that biomass normally would be emitted in, the carbon would be emitted in landfill, but we're storing it. So we can actually be a net carbon negative using this technology. Finally, well, one last route is the innovative DRI route. This is the most promising route for decarbonization, but again, it's dependent on massive quantities of green hydrogen being available. And we have a pilot site in Hamburg, and the production for this pilot facility is expected to start in 2023. So I've just briefly skimmed over our decarbonization efforts, but we published reports that go over these technologies or efforts in much more detail. So you just have to Google ArcelorMittal Climate Action Report, and you'll find this report very easily. And the other reports, that are integrated annual review that provides a lot of information as well. So one other thing I want to mention is that the best way to decarbonize is not to produce the emissions in the first place. And one way to do that is to reduce the amount of steel that we're using in our steel end-use applications. So we've been doing this for years in the automotive sector. I remember when I started working at the FASCO 20 years ago, the average tensile strength of product going into the automotive industry was about 600 megapascals. Today, we're producing massive quantities of 2,000 megapascals. And the result is that we can produce stronger, lighter, and much more carbon efficient cars. So we've been doing this for several years, and this program is called S in Motion. And our crowning achievement there has been when we were able to convince GM to stick to steel after Ford decided to go to aluminum on the F-150. So we're able to show that the steel truck is much more material efficient, more cost effective, and the embodied carbon is much lower when you look at it from a life cycle perspective. So it was a very successful program, and we took what we learned there and we applied it to building construction. This program is called Stellagence, and we've partnered with leading architectural and structural design firms globally. And we asked these structural engineers, I mean, why are you designing your buildings the way you are? And the response we often received was that it's just the way we've always done it. But then we taught them, you just can't do that anymore. We have higher strength steels that can optimize those structures. For instance, in the case of a beam, in a column, a steel beam, quite often it's a 1-for-1 substitution, meaning if you have a high strength 80 KSI steel beam, and you substitute from a 50 KSI steel beam, 50 divided by 80, that's the quantity of steel that can be saved in that column, like greater than 30%. Also, you can reduce your floor joists by a few inches. You may ask, well, what's a few inches? But in a building that's 50 stories high, those few inches add up to saving a few stories. And then, so that's that much less concrete you have to use in the core, that much less material you have to use in the facade. And it all adds up. The impacts are significantly reduced. And when the structure is that much lighter, you have less loads on the foundation, so you can significantly reduce the concrete necessary for quantity of concrete necessary for the foundations. So my last concluding message is that steel is a very carbon intensive material. So we really have to be smart on how we use it. So now I'll let Ray talk about a smart way of using steel, and that's in culvert applications.
Thank you, Stan. If you would just unshare your screen, if that's okay.
Yeah.
You can go ahead, Ray, and click share. That will, all right.
Can you
Awesome,
see
thanks.
that now?
Yep, all good.
Okay. So I'm going to basically just go through the environmental impact of corrugated steel pipe products now and the future plans. And there's a couple of pictures, as you can see down below, of corrugated steel and also structural plate. I think it's important to remember that when you look at environmental product declaration, it is a snapshot in time as to what impact one's product has on the environment, because it can change obviously from year to year, and EPDs are normally done over a 5-year period. So for instance, the next one we will do is in 2023. So again, what I'm showing you is probably a couple of years old, but it's the latest information with regards to the impact. And the declared unit is 1 metric ton. So that's what we looked at. Stan showed you this before. This is the results of our EPD. You would find this on page 8 or 9 of the report, the third-party report that is done. And it's not very easy to understand just by looking at it here. I mean, you have the impact category down the left-hand column, then you have units, you have the product stage, and you have the reuse, recovery, recycling potential. But when you look at some of the numbers there, like in the second line there, ozone depletion potential, 5.06 times 10 to the minus 8. I'm sure all the people who are attending this webinar will understand that, know how to compute it and so forth. But think of how many people don't even understand what that scientific notation actually means. So it's not easy to look at and try to get a grasp of as to, well, what does it all mean? So I'm going to make it easy for you as I walk through the next couple of slides and so forth, because I've done all these calculations and so forth. But that's my one rant about the EPDs at this point in time. My hope is that in the future, when these scientists and environmental and climatologists who do this type of work and engineers and so forth, that they make it a lot easier for the reader to look at. So the results of 1 metric ton of steel, our global warming potential, we would produce 1.5 tons of carbon, which is equivalent to driving that automobile 32% of the year, or driving it at 5,907 kilometers, or heating that home for a quarter of the year, or using 61 propane cylinders for your home barbecue. So let's get a little bit more specific. Let's look at the environmental impact of corrugated steel pipe, and we take an example. We'll use a storm sewer. We use a spiral rib, which is smooth on the inside, ribbed on the outside with a Manning's flow of 0.012. We're going to use a 450 millimeter diameter pipe. The thickness of this pipe is 2.0 millimeter, and 1 metric ton of steel would produce 37 meter length, or 6 pieces of pipe, say, using a standard length of 6 meters, just to show you what we're talking about. So now I'm going to give you the impact on the environment of 1 meter of that particular size, that particular thickness, and so forth. So 1 meter of that particular diameter, corrugated steel pipe would produce 40 kilos of carbon. If you take the same 1 meter of pipe for the same diameter, again, a snapshot in time at this stage in time, a concrete pipe, reinforced concrete pipe, would produce 67 kilos. So again, it would be like driving a car 158 versus 264, or using 1.6 propane tanks versus 2.7 propane tanks. So right now, the snapshot in time is steel is 40% less the carbon footprint of concrete for that particular diameter, 450. Now, if you extrapolate that out from 450 all the way up to say 2400, you'll see the kilos on the y-axis, you'll see the diameter on the x-axis. You start at 450 millimeter diameter, moving all the way to 2400 millimeter diameter. Corrugated steel pipe is the green bar, and concrete is the blue bar. You will see that the green bar does go up slowly, but you can see the rise of the blue bar. So when concrete gets up into the very large diameters, just because of the mass and the weight of it, their carbon footprint increases dramatically over corrugated steel pipe. So if we look at other things besides carbon, there is such a thing as acidification or acid rain. It's measured by sulfur dioxide. For that 1 meter of that particular pipe, corrugated steel would produce 0.29 of a kilo, concrete 0.42 of a kilo. Steel produces about 45% less acidification than concrete. There's a couple of pictures of acid rain down below and what it does to our forests. Another area that they look at is eutrophication. That's pollution of water and soil, or that green that you can see on the water down below. It's just yucky stuff. It's measured by nitrates and phosphates. CSP would produce for that 1 meter of 450 millimeter diameter, 0.012 of a kilo. Concrete, 0.028 of a kilo. Steel produces about 133% less pollution of water and soil than concrete pipe for that particular diameter.
Right, if I may interrupt, there's a question asking, do you have the same comparisons as in between corrugated steel and concrete? The same comparison including PEHD pipes as well?
You're talking about high density polyethylene. At this stage, we do not. And the only reason we do not is we could not find an environmental product declaration out there for HDPE. We could find one for PVC, but PVC is more into sanitary sewer pipes and so forth and the smaller stuff. So we didn't compare ourselves to that. So at this stage, because we could only find reinforced concrete pipe, we compared ourselves to that. And a third party did that, which I'll mention in a minute.
All right, thank you.
Okay. So with regards to smog creation, and everybody knows what smog is, CSP would produce 4.24 of a kilo, concrete 5.1, and steel produces about 20% less smog creation than concrete. And then the last thing I will mention is the depletion of abiotic resources or fossil fuels. It's measured in megajoules. CSP for that 1 meter would produce, would incur 516 megajoules, concrete 1,049. So steel uses about a 103% less embodied energy consumption than concrete. Just on a recent design, I had a question by a consultant just to show you, and I want to show you the impact of, say, a larger diameter and what the mass is versus, say, corrugated steel or spiral rib. It was a recent design, 900 meters in length, 1,500 millimeter diameter storm sewer. And I was asked to compare a polymer laminated material versus a reinforced concrete pipe. Just to show you the comparison, the requirements, a spiral rib pipe, RCP, total number of pieces, 100 for spiral rib, RCP 369, 73% less. Reason for that is spiral rib pipe comes in longer lengths, anywhere from 6 meters to 9 meters in length, whereas a reinforced concrete pipe, you're talking about a 2.44 meters standard length. And then here's the big catch right here. It's the total weight, the kilos itself for that particular job, 80,000 kilos, reinforced concrete pipe, 1.8 million. And so the advantage is 95% less weight. So if you go back to that chart I talked about where you go up in diameter, you get a huge difference with regards to mass. And that's why the carbon footprint at this point in time is so much lower. There are other factors here, total number of trucks, so less transportation and so on and so forth. But I won't go through all of this in detail because that's for another time. So the one that I'm after was what was the carbon footprint or the carbon emissions on this particular job if you were to use spiral rib versus concrete pipe. And the CSP would be 121 metric tons of carbon. Concrete would have produced 405 metric tons. That's like driving that car 476,000 kilometers or heating 21 homes versus the numbers that you can see down below. So in this particular job, steel is 29% the carbon footprint of concrete for this project, or 334% less. If you wanted to, refute what I've said or what have you, this is all backed up by third parties. It's not just me doing my own comparison and my own study and so forth. We've done a lot of work with different companies out there. There's a number of companies in North America who do this type of work with regards to life cycle analysis and so forth. We use SCS Global to produce our environmental product declaration. We used Group Agico out of Montreal, and they did a comparative life cycle assessment of steel versus reinforced concrete pipes. So, and this is where you have three experts. You have a concrete expert, you have a steel expert, and then you have a chair who's a life cycle practitioner and expert. And they review all of the information and more or less confirm or do not confirm the report and so forth. And it's about an 80-page report. And if anybody's interested in looking at it, it's available to each and every one of you. You can go to www.cspi.ca, click on sustainability in the resources section, and you'll find all the reports there for downloading and so forth. A couple of other things I wanted to mention. We have an environmental calculator there also. You can go in and put in the, let's say you're looking at a job and you wanted to know the carbon footprint difference between the two materials. You can, with a drop-down menu, you can put in your diameter in millimeters, starting at say 300, going up to 3,000 millimeters or whatnot. Length in meters, let's say your project is whatever it is. I just put 6 there, but it could be anything you want. So you put those two in there, and it will produce the global warming potential in carbon of tons for CSP and RCP and give you the difference. It will show you the fresh water that is used to produce that CSP versus the RCP. And we'll show you the total primary energy in megajoules that was used to produce those two. And what we've done is we've done an equivalent, because sometimes it's very difficult to get your hands around things like carbon. And how does it equate to something we do each and every day? Well, we drive. So we've equated it to the kilometers driven for a car. For fresh water, again, it's hard to imagine how many liters of water. Well, we've made an equivalent of number of plastic bottles to a landfill site that would go in. Or with primary energy for megajoules, what does that mean? We've made an equivalent with regards to how many smartphones you would charge. And that will pop up each and every time it's being used. So it's also available on our website in the same section. Yes.
There's another question, Ray.
Yes.
Someone's asking, how is the service life, the difference in service life between concrete pipe and corrugated steel pipe factored into that comparison?
It's basically taken into consideration 75 to 100 years material service life. So basically it was looked at with regards to the coatings of the steel, the environments that we have in Canada and so forth, and the thickness of steel that was used. And that's how it was compared. So it was basically a minimum of 75 to 100 years material service life.
Were both service lives equal in the comparison between concrete and CSP?
Yes, that's how they did it. And that's how it's confirmed in the third-party review, third-party study.
Thank you.
So we had to go up in thicknesses and gauges to meet those different, material service lives and so forth. Okay.
Thanks, Ray.
Just to show you some of the things going forward, what's happening with regards to, transportation is a big thing. So alternative methods are being looked at. As Stan mentioned, with electrification taking place, we're looking at electric vehicles. Within the manufacturing plants, our members are looking at retrofit of plants and working towards becoming carbon neutral. Every member in the Corrugated Steel Pipe Institute, who's a member, has committed to the Paris Accord, which Stan has mentioned, being carbon neutral by the year 2050. But many members have taken steps right now to move that plan forward, like electric vehicles, electric forklifts versus using, say, propane or gas. And then the other thing is capturing, recycling, elimination of all natural gas, oils, or lubricants, and propane that is being used in the plants with alternative technology. So many of our members have now, rather than just doing a profit plan every year where they talk about their capital investments and how much they're going to sell and what they're going to do, now the carbon footprint and carbon reduction is now part and parcel of their planning process going forward. One last slide that I wanted to mention to you is about legislation that exists. California, the state of California in the United States, is probably the leader in North America with regards to moving things forward. They have talked about using environmental product declarations to determine if suppliers fall within their stated global warming potential. So what that means is when they put out contracts for tender, they will be looking and drawing a line in the sand and saying, you must meet this so much carbon, for your product per meter or whatever it is, and how they do that. So people are going to have to scramble that if they want to participate in state contracts, they're going to have to meet their guidelines. In Canada, we have what is called with the Canadian federal government, we have what is called the low carbon assets through life cycle analysis. But nevertheless, there's a lot of talk. You hear politicians standing up and, beating their chest and stating that they're committed to climate change and carbon reduction and so forth. But nevertheless, if they don't come up with legislation that drives this and makes it happen, it's going to be a tough thing to see follow through. I mean, yes, we have carbon taxes in Canada, and that's somehow going to think people maybe make changes to their buying practices in the future. But nevertheless, there's going to have to be much tougher legislation to make this happen if we're going to meet the Paris Accord. And the one thing that I mention here is the city of Calgary. In a lot of the conversations and the talks that I have had around the country and so forth, the city of Calgary seems to be very progressive. They are moving to what is called Envision, where they're looking at capturing all of what they do within the city, what they emit, and how they can improve, which will include their buying and their procurement going forward. So, good on you, City of Calgary, and let's hope every other city in Canada, gets on board and starts to move this forward. And that is what we are covering today. Back to you, Amin.
Thank you very much, Ray, and thanks, Stan, for your excellent presentations. I see questions are popping up as you were finishing up. I would like to remind everyone that if you wish to ask your question verbally, if that's easier, just click the raise your hand, and I will be able to have you speak. I see one raised hand. There's just one question that is typed. I will bring that to the presenters, and then I will let you speak the person that's raising their hand. So Ray, based on the data that you presented, it is hard to justify any use of concrete in infrastructure application. So why do you think concrete is still being used?
Let me just say that, first of all, I mentioned it's a snapshot in time. So what happens next month or tomorrow, next month, next year, 5 years from now, and so forth? Meaning every one of us, whether it's concrete, steel, high density polyethylene, PVC, you name it, everybody should be moving to carbon neutral if we want a better planet and so on and so forth. So right now, yeah, we're ahead of the game. But if we do nothing and the other materials do, execute on their plans and do everything and do it better, who knows what those charts will look like 5, 10 years down the road. So yeah, all we wanted to know at this point in time is, if I go back 5 years ago, I've been in this industry for over 40 years. If I go back 5 years ago, I didn't even think about climate change, which was terrible, but I didn't. And we've only started thinking about this probably within the last 4 or 5 years, and we wanted to know where we stood. Were we good? Were we bad? Were we ugly? And we found out that we're not great, but we wanted to know where we stood against who we compete against. So we at least have a starting point. And then when we do this again in 2023, we'll be able to look back and see, are we better? How are they? Are they better? Because they're committed too. I mean, if you look at their websites and so forth, they're committed to becoming carbon neutral also. So we're all trying to get to the same end point. It's just some of us are a little further ahead at this point in time. That's all it is. And their products are good in certain applications, whereas ours are good in certain applications. So all the products are needed. It's a matter of us all moving towards becoming carbon neutral in the future.
I see. Thank you. So I'd like to turn on the microphone for Manny, who has a question. Go ahead, Manny. You can unmute yourself and please be brief and concise.
Yeah, thank you, man. Hi, Ray. This is Manny from region of Durham.
Hi, Manny.
Leading the roads as well as climate change side of things. When you tendered the contract for storm sewers, most of them buried, the contractor has a right to choose the equivalents, and normally they end up using HDPE over concrete or CSP, and unless for culverts in locations where CSP or concrete is necessary. So what's your comment, the way the market demands dictates the material, and without an HDPE in this equation, it's hard to really understand about carbon limiting. Yeah.
Good question. When I started in this industry back in the 80s, or actually late 70s, I didn't understand a lot about the chemistries of soil, the chemistries of water across Canada. And if you go across Canada, it's quite different from province to province. Give you an example. If Newfoundland, very soft water. You go to Manitoba or Alberta, very hard water. So you get a calcium carbonate and so forth that builds up on materials that protects it and so forth. So certain materials perform better in certain applications. And we didn't know this probably until, I would say, the mid-90s, late 90s and so forth. So there are a lot of engineers out there who are still in cities, municipalities, who have dealt with a certain material for a very long time. And if they've had a bad experience with a material because, it prematurely deterioration or whatnot, it's hard to get them to think otherwise and so forth. So, there's so many answers to that particular question. If cities like yourself or municipalities like yourself would open up your standards and allow different materials and different choices that meet your, design service life or material service life, you would see much more competition. You'd probably see better pricing. You'd see, just a better choice of materials. And then you can make that choice, whatever that is, whether it's steel, plastic, or concrete, one of the three. But if you close the door by not even looking at, some materials because of maybe a past experience or a lack of knowledge on what's taken place with different coatings or whatnot, then, you're only hurting yourself and the taxpayers. And let's face it, we're all taxpayers. So we expect our each city to make sure they're looking after us in the best interest. So I hope that answers your question. It's a tough one. Tough one.
Yeah. We have a couple of other questions asking, so the comparison between the steel pipes and concrete pipes, which type of coating was considered? Was it galvanized or polymer covered steel?
It was It was galvanized originally, and then we took it into both aluminized and polymer laminated. So we included both in the comparison. So all three materials. And the thicknesses of steel with regards to galvanized increased for galvanized steel to make the certain life expectancy of what they were comparing concrete to steel.
I see. And also another question asking about the comparison regarding the life cycle assessment. What is the asset life of a steel pipe?
It will depend upon the environment that it is in, the location it is. I can show you pipes that have been in the ground for 80+ years. They're perfect. You take that same pipe and put it into another location, and you know, it might last a quarter of the time. That's why you need a different coating or a different material. But you know, all materials, there's this feeling or out there, that this thing that goes out there that, oh, our pipes last 100 years. You'll hear that a lot from many different companies and organizations. And yes, they do in some instances, but they don't in all instances. It depends on so many different factors. It depends upon chlorides. It depends upon salts. It depends upon hardness versus softness. It depends upon, you know, you name it. We did the webinar on Thursday about rehabilitation. We rehabilitated a concrete pipe underneath the 401, 410, 403 back in 2005 that was 30 years old. Now, if it's supposed to last 100 years, why is it being rehabilitated after 30 years? But it wasn't the concrete pipe's fault. It was the surrounding environment that was around it and the salts that were coming down from the highway, getting in through the concrete, taking out the rebar, and then it was causing issues and so forth. So sometimes the material or the pipe gets blamed, but it has nothing to do with the material of the pipe at all. It's the environment or the chemistries of the water. I mean, when I was a kid, we never put salts on the roads. And look at how much salt we put on the road now. And you think of your car, how long does your car last? If you don't clean that salt off every year, I don't see many cars running around here for 100 years. So it's like anything, you know, you can go and pound your chest and say it'll last 75, 100 years, but yeah, it will in many instances. But in some locations, that's not the case. That's not true. You know, it's not.
Right, for the LCA study, I believe we used 75 years because that's,
Yes.
if I recall, that's the minimum that the standards have.
That is correct.
For both applications, concrete and
You're
steel.
right, Stan. It was 75 years because that's what the DOTs require. Most of the DOTs require 75 years minimum life. One other thing to also consider, and maybe I'm ranting now, but I'm just, you know, it's nobody ever cleans these things out. Nobody goes in there with a pressure washer and washes off the salt and so forth, like you would your car or what have you. Out of sight, out of mind. It gets buried, and there's very little maintenance that's done when things are buried under the ground. Think of how many bridges, say, above the ground are, you know, rehabilitated on an ongoing basis. Things below the ground, not often.
All right, thank you, Ray. I don't see any more questions coming in, and we're exactly on time. So with that, I would like to thank Ray and Stan again for their excellent presentations on this timely topic. And I would like to remind everyone that the recording of this webinar will be made available online on our YouTube channel, and we will check with the presenters, and if everything is in order, we'll share the slides with everyone to make them accessible. And with that, I would like to thank everyone that joined us today for their time. And once again, thank you, Ray and Stan, for volunteering your time and presenting on this timely topic.
Thank you, and thank you all for attending. Truly appreciate it.
Thanks, everyone.
Thank you so much. Have a good day.
Thank you, Amin.
All right.